setting up the optimization using the reactive response surface method to maximize the efficiency and pressure ratio and range of the compressor. We use 8 input parameters to control the 3D blade shape, the distribution of blade loading at the hub and shroud, the position of the leading edge, the height of the blade at the inducer, and the tip width at the extruder. We are also allowing the blade stacking angle to vary. This enables chevron at the trailing edge, which is often used to suppress secondary flow at the rotor exit. We constrain the throat area to maintain the same swallowing capacity for the rotor when it is being optimized. For the objectives, we want to maximize efficiency at the surge side and choke side of the map, which should extend the map range on both sides. Holding or increasing mid-map pressure ratio stops the map from flattening. That is, increasing map width at the expense of pressure ratio delivery. An initial design matrix of 24 candidates establishes the design space topology. RRS with CAE then adds 20 additional points to be run in CFD. So 24 plus 20 times 3 for the 3 operating points gives 132 CFD calculations. This fully automated process took 30 hours on 4 computational cores. We see in the top left figure how the optimizer, after generating the initial design matrix of 24 candidates, homes in on the optimal. The top right figure shows the complete design space for 2 of the 3 output objectives. The optimum lies in the top right corner. So this is where the surrogate model constructs the Pareto front. The bottom figures show the Pareto front constructed by the reactive response surface method. A reminder that we are looking at a 3-dimensional Pareto front in a 2-dimensional plot. All the points shown in the bottom 2 figures are Pareto-optimal between the 3 objectives. So we can select an optimum design from this front. Now let's take a look at the Turbo Design 1 GUI, setting up and running this study. We are able to set up export objects for a number of different formats, including STEP or iJust solid models and TurboGrid curve files. The type of export will depend on what CAE analysis system we will be using. We select the CFD solver we want to use, in this case, ANDA CFX, and the step export that we have just created as the target case. Then we choose the solver settings, the target Y plus in the mesh, the turbulence model, the number of computational cores, and the convergence criteria. Then, we define the number of operating points we wish to run in this simulation set. For each operating point, we define the boundary conditions, which can be pressure or mass flow based. Once we have this CAE integration object defined, we simply select Run on the object and the analysis that all the defined operating points will go ahead. Turbo Design 1 automatically handles all the meshing, pre-processing, solver monitoring, and post-processing. Once the analysis is completed, the results are automatically returned to the Turbo Design 1 project manager, giving us our baseline characteristic. We are now ready to run a multi-objective, multi-point optimization on this case. We are going to run RRS with CAE to exploit the machine learning algorithm using a small but high-fidelity dataset. First, we define the optimizer input parameters. Blade loading at the leading edge and the slope of the blade loading distribution, 3 meridional geometry parameters, and the wrap angle at the trailing edge. Turbo Design 1 can estimate the ranges of the input parameters via the feature estimate input ranges on the optimization object. By using this feature, the software automatically employs a machine learning algorithm to calculate appropriate lower and upper bounds on the design space. We can define constraints for the optimization, which will mark candidates that fall outside of these constraints as non-feasible. In this case, we constrain the throat area to within 10% of the baseline. This should help to control the position of the peak efficiency on the speed line. Next, we define the objectives for the optimization. Because we are integrating multi-point CFD runs into this study, we can choose CFD results as objectives. We want to maximize efficiency at the surge side and choke side points, and maximize pressure ratio at the design point. Finally, we set the optimization meta-parameters. The initial DOE size, the number of response surface search iterations, and how many extra points to add after each iteration. We are now ready to run the optimization. As the study progresses, the design space is populated by the CFD runs, initially as a DOE and then as a gradient search. After each iteration of 4 new candidates in CFD, the response surface is refitted, and the optimizer reassesses the route to the optimal solution using a genetic algorithm. You can see how the optimizer rapidly converges onto a solution whilst constructing the design matrix. In this case, 4 candidates were tagged as non-feasible, violating the throat area constraint. So in the end, 44 candidates were assessed at 3 operating points, giving 132 CFD runs. This took 30 hours on just 4 computational cores. After the iterations are completed, we can see the relationship between inputs and objectives, or between competing objectives. Shown is a surrogate model Pareto front based upon the design space topology created by the CFD. Each individual candidate in the design space can be selected for further analysis, either in Turbo Design 1 or go straight to further CFD analysis. Our selected candidate can then be compared against the baseline or any other candidate.